Hello and welcome to another session in the Mind Grid. Today, the topic is first part of a multi-part series where we introduce networking concepts, and this uses myHDL, which is a Python-based version of a way to write HDL code and model your HDL using Python. In this part, we're going to be talking about layer 2 Ethernet parsers. All right, so in terms of our goals today, our goals will be to describe how the networks operate, how to design blocks of these networks, and then how to simulate and debug using myHDL. If you have not seen myHDL or not familiar with myHDL, I will leave some links. I have made other videos about what myHDL is, how to install and how to use it, and it's definitely a very useful tool. All right, so what is networking OSI model? OSI model is a very well-known stack in networking where all the networking functions are divided into 7 layers, and the physical layer being the first layer, which is at the bottom where the bits actually travel the material, the media, like optical fibers and copper cables and so on. Above that is a data link layer that manipulates packets at the lowest level, which is just Ethernet today, commonly known. Other technologies are like SONET, ATM. They also existed. Then there is the network layer, which obviously we are familiar in terms of like IP addresses and such. So routing of packets over long distances is taken care by a networking layer. And then above that are other layers like transport, session, presentation, finally application. Most people are not really aware because they are, in most cases, working in a specific layer. And so they are just dealing with the intricacies of that layer. But in general, network design requires a deeper understanding of these layers to be able to design the application that you're targeting. Now, in most cases, when we talk about hardware design, we'd be talking about lower layers because the hardware is simpler in these layers and can operate at very high speeds. The division of processing is very clear in this, but when we design different algorithms that operate at very high speeds, we are usually designing algorithms for a specific layer. All right. So with that, let's dive into what the Ethernet layer is, because that's the topic of today's discussion. The Ethernet layer consists of certain structure headers, and then they carry some data. And then at the end of that, there is a frame check sequence, which is a CRC that makes sure if there's any corruption in the data, you can figure out that the packet is corrupted and throw it or discard it. So in the beginning, there is a preamble. Preamble is just a predetermined sequence that precedes the packet. Then there is a destination address, which is where this packet is headed, source address, which indicates where this packet is coming from, the type, which may indicate various types of packets, like, there could be IP, there could be maybe other types of packets, and so on and so forth. Now, there are different formats here. There could be IEEE standardized format, which may have slight differences, but in general, this is how the packets look. Now, the type also could be, the type here, the type field could be also a length in some cases, and so you have to interpret it accordingly. Okay, so now that we understand what Ethernet packets are, our next goal is to build this algorithm that is to strip GRE packets. Now, GRE is a tunneling protocol that happens at layer 4. And so we need to be able to find where the layer 4 is, what is inside layer 4, be able to strip the GRE layer and then recombine and form the new packet. And that's going to be our main goal in this series. And so we'll start building that block by block. All right, so with the block diagram in the view, let's look at what our layer 2 will look like physically, because we understand how the OSI model talked about it, but now we actually look at what it looks for the hardware designer. So obviously there's going to be a clock with certain frequency, and there's going to be data. And data is not going to be just one bit, it's not going to be one byte, it's going to be very wide bus, because we have to carry so much bandwidth So if let's say the clock is 400 megahertz, 500 megahertz, you have to have data which is at least 256 bits wide so that you can carry certain, let's say 100 gigabits. So we are designing, let's say for 100 gigabits, and there you would have the data to be 256 bits and maybe 400 megahertz clock or 450 megahertz clock, whatever you have, right? So you have to do some calculations to make sure that your data and clock are appropriately sized for the data pipe that you're designing to. In this case, we are designing for 100 gigabits, and so that's sized accordingly. Then there is start of frame. This is a start where the first byte of data lies. End of frame, which is where the last byte lies, and usually start of frame is aligned with the MSB, the first byte, so we don't have to indicate where exactly the packet starts. But depending on your use case, maybe you need another indicator, like here a tag, which says when the UF happens, what of these 32 bytes or 256 bits we have, which byte is the last byte. So in this case, it might say that byte number 13 maybe is the last byte. And then once the parsing is done, the goal of L2 parser is to indicate where the L3 lies, the IP layer or the networking layer, where does it lie? So it's going to parse and figure out where that lies and indicate with the start of frame for that layer, and also indicate exactly which byte is where the start of the frame lies. All right. So with that, now we have understood how the frame is organized. Now let's take a quick peek into what the data looks like normally, and then we'll dive into the code and start analyzing the code. So the data looks like this. I said there are 32 bytes. Now byte are organized from MSB to LSB, where D31 is the topmost byte. That's the first byte that you see, and D0 is the last byte that you see. First byte is at 255 down to 248 and so on. Last byte is 7 down to 0. So you have 256 bits given to you in every clock cycle. And there is a tag. Like we said, when the end of frame comes, we indicate it where exactly the end of frame lies, which byte. So if it lies on the very first, we say tag is 0. If it lies on the lowest byte, then the tag is 31. So that's our interpretation. Now, the tag value is very interesting because if you see the number of valid bytes, you can just take the tag and add 1 to it. So if it's 0, it contains 1 valid byte. If it's 31, then it has 32 valid bytes. So all of the bytes on the byte lane are valid, right? The first clock cycle is a special clock cycle in this design because we put some metadata at the top. So there is like 16 bytes of metadata, and then the actual packet starts. So the packet is slightly aligned in such a way that you have space to carry some extra headers. These headers may be able to squeeze in any packet related information, routing related information. And so as the packet traverses our algorithm, we can do some processing, extract some data, and stick it into this space that has been created for us so that we don't have to store it somewhere else like out of band. We can store it with the packet. So every packet carries its metadata. And this is just a convention. You could have made any amount of metadata. It could be a clock cycle wide where it'd be 32 bytes. In our case, we have 16 bytes of metadata preceding the packet, and the packet starts. All right, so I think that's all I had here for the slides. Now let's dive into some of the code. So this is the code for the L2 parser in myHDL. And obviously, this is, if you haven't seen myHDL before, look at my previous video that shows you how to install and use myHDL and get it started. Now here, once you've imported everything, you start your first block, and this block is called parser L2. This is the parser block, and what it does is that it has clock and reset as usual, and then you have what I have organized my signals is in these structures. So L2IF is a structure that brings the L2 signals, which I have showed you earlier. I'll show you again. L2 extract is whatever data we have extracted in this clock cycle. L2IF is the output interface, which is the output of L2 parser, and L2 based signaling, layer 2 based signaling, and then at the output of L2, the L3 based signaling. Now let's quickly dive into a block called package, and that'll tell you what these L2IF and L2IF extract, all these are. So if you go to a file called packages, I'll see package, right? So here you can see that this is a class that we use to define some of the bundles. So L2IF is basically SOFUF tag and data, right? As we described in the diagram, these are the signals Now L2 IF extract, if you look at L2 extract, we extract the source address, destination address, the type, VLAN, values, etc. So this is the extract function. This is the extract bundle or class. And we can, as you can see, that we have figured out a way to pass all these uh, into our function, into our module, right? So now let's find our way back to the parser L2. Parse L2, let's see where it went. We probably have it here. Okay, parse L2. All right, so that's a little bit about the interfaces, L2 interface, L2 extraction interface, L2's output interface, and the L3 output interface, right? So these L2 comes in, and then when we extract all the L2 data, it becomes L2 extract, and then it then passes on the signals to the next block, which is the L3 parser. So now, in terms of state machine, we have two states here, idle and data, and we define a state variable so that we can do the state machine. And this is just initial block. We don't really need the initial block here. We could have basically just deleted this. I think we could just as easily delete this stuff. I don't think we need any initialization in this module. All right, so then you have the state machine. If reset, the state goes to idle. And then basically in the idle state, what happens is that if you get an SOF, then you extract the destination in certain values, right? Shows you how to extract it. Certain bits and bytes, like 128 down to, whatever, 80. And 128 is non-inclusive, so you have to understand how this bit select works. But essentially what I've done is that I've extracted destination address, source address type, and I've stored it into this L2 extract data structure. And if the L2 extract type is, if VLANs, right now the VLAN code has not been added here, but if VLANs come, then you could handle the VLANs. But if there is an IP packet, either IPv4 or IPv6, then we produce the SOF and we set the tag. Now this tag is based on the fact that this current alignment is such that we have found it in the packet, and we have found it right after destination source type. We have found this type, right? So we extract it this way. We indicate the L3 SOF, and we go back. We go to data, and in the data state, we just wait for the EOF to come, and we go back to idle and wait for the next SOF. Excuse me. So that is essentially the state machine, and that is all that is in this state machine. So how do we compile it? We just have to run Python on our test bench, and that should compile this. And so it compiles this, and then we essentially just run the GTK wave, because this VCD file has been created for us. So what we're going to do is we're just going to, let's just, I'm running Wireshark here, so I'm going to start the GTK wave. And in this GTK wave, I'm going to load the signals that I've already defined, which is for L2. So now you can see these are the signals. This is the input interface. So the first clock cycle, as I showed you, in the first clock cycle, you got a bunch of data. You got the meta header, and then you got this packet starting at 128 bits down to 0. So the packet started there, all the bytes are there. In the first clock cycle, you get 32 bytes, out of which only 16 are header, and remaining 16 are on the packet. And then you have the next clock cycle, the next clock cycle, and the next clock cycle, and finally an EOF. And EOF says at 09, I think this may be hex. So we have to actually convert this to decimal. That'll tell you, if you put this decimal, that is 9. So byte number 10 is the EOF at byte number 10. So this is the input. Now, if you look at the output interface, it basically has extracted the destination address, the source address, the type, which is 0800 is an IP packet. So it has extracted all this, and it has aligned everything. Look, there is a delay between SOF and the output SOF. It has also created L3 SOF and the L3 SOF tag, right? So it has created all that data from the input data, and it's been able to output all this. So this kind of looks like, if you've done your simulation in Verilog, it kind of looks like that. You have all that capability and the convenience of modeling it in just in Python. You don't need any licenses. myHDL is fairly easy to use. And so that is what you got. Now, one more thing I can show you is that, see, we have these destination and source MAC addresses. Let me see if I can start Wireshark here. So I might be able to start Wireshark here. Just 1 second. So if I say Wireshark GRE, okay, so let's see if we can open Wireshark from here. And Wireshark open. So now you can see that the Ethernet destination address is 0CB052, and what we have extracted here is 0CB052. So we have extracted that destination source and 0800. So we can show you that as well, that the packet type is 0800. So our L2 parser has worked flawlessly. It has produced the values as expected. Now, one thing I want to caveat this is that, as you saw, we don't have VLAN parsing. So one could easily add the VLAN parsing. If there is VLANs, you could maybe make those changes to the state machine and be able to support this. So this is a quick intro into the networking first part. We talked about L2 parsers. We talked about how Ethernet operates as the layer 2 of the OSI stack. And we also showed how myHDL, which is a Python-based port of ability to write RTL code in Python, essentially. So we saw how all that works, how we are able to simulate it, and how we can make sense of this and actually combine everything to model our algorithms. Now we will continue on in the series and continue to layer 3 parser in this series next. So stay tuned, and until next time, take care and bye-bye.